So in this video, we're going to use natural logs to find the derivatives of certain functions. And the first couple examples we already have natural logs built into them. So what we're going to use is we're going to use the expansion of natural logs. So exponents swing out front to ln of 2x plus 3. And then division is subtraction, so minus ln of x minus 4. Now, what we need to know is what's the derivative of a function now. Let's just use x right now. And the idea is you put the derivative, x prime, which is 1 over the original. So if we're doing the derivative, I think the book has this in terms of just u, we're going to have du over u. Okay, so the derivative goes on the top. So this 2 that's out front here is just out front. You don't have to do power rule or product rule or anything like that. Times, well, the derivative goes up top, so 2 over the original, 2x plus 3. And over here, minus the derivative, which is 1 over the original. And there you've got it. I mean, the only thing I'd still would do is I would make that a 4, but that's really it in the end. So if you've got something with natural logs, you don't want to do something like nasty chain rule with a quotient rule in there at the same time. You really want to expand and then take your derivative. Now over here you're looking at some crazy chain rule, some crazy product rule. Let's get this cosine cubed, they have to drop down, derivative cosine, sine, all that fun stuff. But what we can do is we can write this as natural log of sine plus 3 ln of cosine of 2x. Now, I can't really break up the cosine of the 2x. I can't expand that much because of them. And so we do our derivatives. Derivative of sine is cosine, and there should be an x on this. Cosine of x divided by the original, sine of x, which is tangent, which kind of gives you one of the reasons why the antiderivative of tangent is, well, it could be just this one. There's more than one kind of answer for these. Oh, sorry, this is cotangent. So the antiderivative of cotangent is natural log of sine. Plus 3, derivative of cosine is negative sine. But it normally would be x, but now it's 2x times the derivative of the inside, which is 2, over the original cosine of 2x. And again, we can clean this up and make this a 6 instead of a 3 and a 2. Okay, so what happens if you don't have the natural log on one of these problems? So don't get me wrong, you don't have to do this for a problem like 5 or 6. You can, especially in 6, I'd probably just do the quotient rule. But anytime you get some really nasty nested looking thing, natural log differentiation might be the way to go. So what we're going to do is we're going to take the natural log of both sides. And I'm going to write this as x plus 2 to the 3/2. Treat that square root as 1/2 exponent over x minus 6 to the 4th. And then you can break these up. 3/2 ln of x plus 2 minus 4 ln of x minus 6. And technically I should have parentheses around these. And the other side still just ln of y. Now the right side looks fantastic. I mean, I've taken this crazy quotient rule with inside of a chain rule and turned it into, well, just 3 over 2 x plus 2 minus 4 over x minus 6. The problem with this is the left side is not just y prime. It is y prime over the original. The derivative of y, which is y prime, which is what we're looking for, over the original. So what we want to do is get that y out of there. Now, I don't want to multiply the right side by y. I want to multiply the right side by what y is. The original function. Square root of x plus 2 cubed over x minus 6 to the 8th. So in the end, you can't forget you have to multiply through by the original. And yes, you could distribute this and probably simplify it down a little bit. I don't know if you really could simplify it much. But like the x minus 6 to the 8th, that becomes just the 4th. And you could do something with that, but I personally would leave it just like this. And that's one of the hard things on the multiple choice on the multiple choice on the AP exam is they may not have it quite set up the way you do. This might be your answer, and they might have some distributed thing or some factored out thing. I don't know. But that'd be the answer I would expect. All right, let's try it one more time here. ln equals, and if you can start kind of doing some of the rules at the same time, maybe like natural log sine of x minus ln of cosine of x, it's division subtraction, that'll help you out. So you get y prime over y equals, well, natural log of sine of x, the derivative, is cosine over sine over the original, derivative over the original, minus derivative of cosine is negative sine over, well, cosine of x. And then what we have to do is we have to multiply through this by y. So all this by sine over cosine. Now, I guarantee you this is not what you would see on the AP exam. This would not be the multiple choice. What is y? Y is really tangent. And I kind of expect to see secant squared, right? Okay, so let's see what happens when I distribute. When I distribute the first part, I get a 1 plus sine squared x over cosine squared x. Okay, well, 1 plus tangent squared of x is secant squared x. So that's the answer. And that's kind of one of the reasons why this is the derivative of tangent secant. You can also, I would just do the quotient rule or try to do this off memory. But you still can do it this way. Just another way of thinking about it. So that's what you do when you take the derivative. If it has a natural log, you expand. If it doesn't, you have the choice of either doing a chain rule or doing the natural log of both sides and expanding. If you're going to choose this way, and I really only choose this way in a problem like this, something crazy where I really would not want to do the quotient rule. This one, quotient rule, for sure. Or realizing it's tangent, the derivative of tangent secant squared, for sure. But for something like this, the natural log would be good. The big thing you don't want to forget is it's going to be y prime over y on the left side. And you're going to have to multiply that y over, which is the original equation. Okay, so that's how you take a derivative. Now the antiderivatives are a little bit different.